Hello, Integrated Math 1. Welcome to lesson 2.3.2b. So we're actually on module 2, topic 3, lesson 2, but we're doing the second half of it. We're doing the second day of it. So we're still looking at linear combinations, and we found that linear combinations are really, really cool, that we could add our equations together, make sure they're in standard form, add them, and that we have some additive inverses, also known as opposites. And then we could add our equations together to eliminate one of our variables to make it easier to solve for the other one. So it was a great method. Again, one of my favorites, just a great method to use. So we're going to continue working with that today. So we have a whole new situation here. The Let It Snow Resort offers two winter specials, the Getaway Special and the Extended Stay Special. The Getaway Special offers 2 nights of lodging and 4 meals for $270. The Extended Stay Special offers 3 nights of lodging and 8 meals for $435. So what we're going to do is we're going to determine what Let It Snow charges per night of lodging and per meal. We're going to work through this step by step. So first of all, the first thing we have to do, it's the first thing we have to do, you're going to need to write the system of linear equations that represents the problem situation. So let N represent the cost for 1 night of lodging at the resort, and let M represent the cost for each meal. So write your equations in standard form. Go ahead and write your 2 equations, one for the Getaway Special, one for the Extended Stay Special. Hit pause, write them out, and then hit play when you're ready to check your work. All right, so let's see how we're doing. Let's start with the Getaway Special. So the Getaway Special, here it is. It offers 2 nights and 4 meals for $270. All right, so that means 2 nights plus 4 meals, and together, that's why it's being added, it's going to be $270. Of course, the other option here is the Extended Stay Special, and they offer 3 nights and 8 meals, so 3 nights plus 8 meals, and together it's $435. And here we have our lovely system of linear equations. Yay! We do like to put a little bracket on it so we know that these come together, that this is our lovely system. So we've written our equations. They are definitely in standard form. We don't have x's and y's. We have n's and m's, but it still works and it still does the job. Now, remember the deal that in order to solve these, we needed to have an additive inverse for the coefficients of one of our variables. And it actually didn't matter which one it was. You could multiply an entire equation by a number or multiply both equations by a number in order to make this work the way you want it to work. It's kind of up to you. So that's what you're going to do. Before we get there, we are going to get there. First of all, how are these equations the same? How are these equations different? So what's the same about these equations? What's different about these equations? Just pause real quick, write down your thoughts on that, hit play when you're ready to check your work. So both equations are in standard form, and that's generally what we like if we're going to use linear combinations. We want our equations in standard form. And the difference is, of course, the coefficients, right? My coefficients for n, my coefficients for m are different. Different number of nights, different number of meals. So they're going to be different. That's just how it's going to go. So what I would like you to do now is I would like you to solve this lovely equation, this lovely system of equations. Use linear combinations. Again, you can either multiply one set of equations, you can multiply both equations, whatever works for you, but multiply something to rewrite it so that you can get that lovely, lovely set of additive inverses of opposites. Go ahead and hit pause. You may need to flip back to notes from last time on how we did this, but hit pause, work this out. Don't forget you need to find both N and M, and then hit play when you're ready to check your work. Now, there are many ways you could do this. For me personally, I looked at this and I thought, you know what? 2 and 3 are not opposites. And yeah, I could multiply both equations to make 6s out of them, and I could do that. But I noticed that if I doubled 4, I would get 8. So I thought, you know what? I can multiply this equation, both sides, by a -2. So that's what I'm going to do. So -2, and we'll distribute that, times 2n is -4n. -2 times 4m is -8m. And of course, -2 times 270, I believe that's 540. I better grab my calculator and make sure. So 270 times a -2 gives me a -540. Yeah, it does. Good. And of course, we still have this other equation. So I still have my other equation. That hasn't changed. So 3n plus 8m equals 435. And look at that. We have additive inverses. Hooray! So let's go ahead and let's add our equations together. These, of course, cancel out. That's why we did it. That's one of the big advantages here. And it looks like then -4n plus 3n, that gives me a -1n. And again, I'm going to use my calculator here. -540 plus 435 gives me -105. Oh, I think we're good on what to do next. We need to get the n all alone, right? So I'm going to go ahead and divide both sides by a -1. Make that cancel out. So I have n, and a negative divided by negative is a positive 105. Now remember, we have to find both n and m. We have to find both of these things. So I'm now going to take this lovely little guy here, and I'm going to plug him into one of these equations. It doesn't really matter which one, so I'm just going to pick one. So instead of 3n plus 8m equals 435, I'm just going to plug in this lovely 105. So 105. And again, I love my calculator. So 3 times 105 is 315 plus 8m equals 435. I do need to get the m alone, so I'm going to go ahead and subtract 315 on both sides. That's okay, that's what we do. So I now have 8m, and let's see, 435 minus 315 gives me 120. And last but not least, let's go ahead and divide by 8. That cancels out. And now I have m equals 15. Yay! So I got n equals 105, m equals 15. If you wanted to, you could write it as an ordered pair. We've certainly done quite a bit of that. If you'd like, you could write it that way too. Yay! Now again, this is not the only way you could have solved the equation. I actually have a totally different version of it here if you want to see it. Oh, hang on, let me do this. Oh, it goes away. I decided to go ahead and make 6s out of these, so that's another option that you could have done. So I multiplied this whole equation by -3. I multiplied everything on that equation by 2, and then the n's canceled out, found out what m was, and then I took my 15, yeah. And then I took my m, plugged it back into one of these equations. I plugged it in here, multiplied, subtracted the 60, and divided. I still got the same answer. I still found that n was 105 and that m was 15. Just changed the order in which I found them, but that's okay. So now that we have these numbers, can you just real quick remember what m and n stood for? Can you real quick on number 4 write down, interpret the solution of this linear system in the problem situation? What do these numbers mean that we found? Go ahead and take a moment, hit pause, write it down, hit play when you're ready to keep going. So if we recall correctly, N stood for nights and M stood for meals, right? So this means that the Let It Snow Resort charges $105 per night of lodging and $15 per meal. Now, if you want to double check your work, there are many ways of doing it. One of the ways of doing that is just plugging into each equation. Plug into each equation and make sure that it works. Plug in for N, plug in for M, make sure that this side adds up to 270. And do the same thing for the other equation as well. Plug in for N, plug in for M, and make sure it adds up to 435. Go ahead and hit pause, plug them in just to double check, make sure we did everything right, and then hit play when you're ready to check your work. All right, so we said it was $105 per night and it was $15 per meal, so I plugged those in. Of course, 2 times 105 is 210. 4 times 15 is 60. Oh, and 210 plus 60 does add up to 270. So hooray, ta-ding, that's a good sign. Let's check the other equation as well. So we'll do it again for our other equation. Instead of N, we'll put in 105. Instead of M, we'll put in 15. So 3 times 105 is 315. 8 times 15 is 120. And 315 plus 120 does give us 435. So this is a great way to verify your solution, to double check that it works. Remember that your solution has to work for both equations. That's why it's important that we plug into both equations and check both equations, because a solution for a system of linear equations must work for both equations. If it only works for one, then we did something wrong. It has to work for both of them. So that's why it's important to plug in and check for both equations. And just real quick, let's round it up. Is the extended stay special the better deal? Is it? Are you actually getting a better deal if you do the extended stay special? And tell me why or why not. Go ahead and hit pause, write it down, and then hit play when you're ready to check your work. So I don't know about you guys, but if it doesn't matter if you're doing the getaway special or the extended stay special, if you're still paying $105 per night and $15 per meal, then the extended stay special really isn't a better deal, right? It's the same deal that you're getting with the getaway special, just paying more because you're staying longer. So no, the Let It Snow Resort charges the same amount for meals and lodging for both specials. And maybe that's nice. Maybe, it's better than if you don't do either special. I don't know what their regular rates are. You'd have to ask them. So let's make it a little more interesting here. Let's make it a little more interesting. Activity 2.4. The school spirit club is making beaded friendship bracelets with the school colors to sell in the school store. The bracelets are black and orange. It's like a Halloween school, and come in 2 lengths, a 5-inch length and a 7-inch length. The club has enough beads to make a total of 84 bracelets. So far, they have made 49 bracelets, which represents half the number of 5-inch bracelets plus 3/4 the number of 7-inch bracelets they plan to make and sell. We want to determine how many 5-inch bracelets and how many 7-inch bracelets the club plans to make. Is your head spinning? Do you feel like there were a lot of numbers there? So let's do this. Instead of 5-inch bracelets, can we just call those X? And instead of 7-inch bracelets, can we just call those Y? So that at least removes some of the numbers. So I'd be like, you're X, you're Y, right? And it could be like, that's X, that's Y, right? And maybe that'll make it a little easier. That's X, that's Y. Maybe it'll make it a little easier to put this together in a system of equations. So go ahead and write a system of equations. Again, standard form seems to be the easiest way to manage this. So write a system of equations in standard form to represent this problem situation. Go ahead and hit pause, work it out, and then hit play when you're ready to check your work. All right. So we have a lot going on here. So I'm going to use a couple different colors so I can keep track of stuff. So the club has enough beads to make a total of 84 bracelets. So if I take my number of 5-inch bracelets and I add my number of 7-inch bracelets, which is y, together, that should give me 84. All right. Wow, one equation down. Okay, well, that was great. But wait, there's more. Order now, and we'll throw in another equation absolutely free. You can't help that. Now, this is the other side. So far, they've made 49 bracelets, which represents half of the 5-inch bracelets, plus 3/4 of the 7-inch bracelets. Okay, so I know together, I've got 49, right? That's how many they've made so far. And that's half of my 5-inch bracelets, my X, plus it's 3/4 of my 7-inch bracelets, my Ys. Oh, look at that. So that actually wasn't so bad. Oh, that wasn't so bad. I mean, yes, we have fractions, but fractions happen. It's just life. So that's a lovely set of system of equations that we're going to use to help us solve this. Now, that's well done. Karen says, and I have my system down here in the corner so you can see it. Karen says that the first step to solve this system is to multiply the second equation by the least common denominator, LCD, of our fractions. Jacob says that the first step is to multiply our first equation by -1/2. Who's right? Go ahead and hit pause, jot down your thoughts on this, and then hit play when you're ready to check your work. So it turns out both are correct. We've talked many times about how there's a lot of different ways to solve these. Both are correct. Karen didn't like the fractions. And she was like, you know what? If I multiply everything by 4, that will make the fractions go away. Fair enough. So she wasn't wrong. Karen chose to multiply by the least common denominator to rewrite that second equation without fractions. And then she'll just have to multiply one of the equations by a constant to create those additive inverses, those opposites for either the x or the y term. So she's not wrong. That's a way of doing it. Jacob's way is correct too, though. Jacob's like, you know what? Fractions are fine. I can deal with fractions. So Jacob was like, you know what? Forget that. I'll work with the fractions. So he chose to work with the fractions for the second equation. So by multiplying that first equation by -1/2, he creates those additive inverses for x to cancel them out so that he can then just work with the y's. So again, more than one way of doing this. But I know you guys. I know you like Karen's way better. I know you don't like fractions. So can you take care of that first? Can you multiply this whole thing by something to make those fractions go away? To rewrite the equation with fractions as an equivalent equation without fractions? I think I may have slipped and mentioned to you what number you could use to multiply everything by to make this work out for you. So go ahead and hit pause, see if there's a number you can multiply your entire equation by to make the fractions go away. Work that out and then hit play when you're ready to check your work. All right, so yeah, let's multiply everybody by 4. I did mention it earlier. We said, hey, 2 goes into 4, 4 goes into 4. So you know what? That is our least common denominator. So let's multiply everybody by 4. I'm going to distribute here. Half of 4 is 4. I'm going to try that again. Half of 4 is not 4. Bad missed up. Half of 4. Oh my gosh, get my pen back. Half of 4 is 2. So 4 times 1/2 x would be 2x. Plus, well, if I multiply these guys together, the 4's will cancel out. And I'm just left with 3y, which is really nice. But don't forget what you do to one side, you have to do to the other. So 4 times 49 gives me 196. And now there's no more fractions, right? I mean, that's not a bad thing. That's not a bad thing. No more fractions. I'm okay with that. Yay, we rewrote the equation without fractions. So now that you've done this, now that we've set you on your way, we've got you started here, let's go ahead and I'm going to rewrite it now, right? So we had, this was our first equation, x plus y equals 84. We rewrote our second equation, right? So that it was 2x plus 3y equals, what was that, 196? Yeah, 196. All right, so we've rewritten it. Solve this bad boy. Use linear combinations to solve this guy. Go ahead and hit pause to work it out, and then hit play when you're ready to check your work. All right, there's more than one way of solving this, people. There's more than one way of solving this. I see a 2, so I could multiply this whole equation by a -2. I see a 3 here, so I could multiply this whole equation by a -3. Both ways will get you what you want. I'm just going to go ahead and multiply both sides by a -2. So I'm going to get rid of my x's by multiplying both sides by a -2. So -2 times x is -2x. -2 times y is -2y. And of course, 84 times a -2 equals -168. Of course, we still have this equation, 2x plus 3y equals 196. And of course, we're going to add our equations together so that these will cancel out. That's why we multiplied with that -2 to the first equation, right? And then of course, oh, hang on, I'm good. -2y plus 3y is just 1y, and I don't really need to put the 1 in front of it. I mean, I guess I could if I wanted to, but it's not necessary. -168 plus 196 tells me that y equals 28. But remember, to solve a system, you have to find both x and y. I've only got y. So let's take our lovely little y here. I'm going to take our lovely little y, which is 28, and I'm going to plug it into an equation. Pick one, anyone. I'm going to pick this one. It seems nice. Oh, except, sorry, it doesn't go there. Bad, Miss Scott. That's y. I almost plugged into the wrong place. So we need to take this guy, and we're going to plug it in for y. So instead of x plus y, we're going to do x plus 28. And that equals 84. So I'm just using my original equation. You could use the second equation if you wanted to. Shoot, you could even go back and use the equation with the fractions on it if you really wanted to. I don't want to. I'm going to go ahead and subtract 28 from both sides. Dun, 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 dun. And I get x equals 84 minus 28 is 56. Yay. And again, you could write it as an ordered pair if you wanted to, 56, 28. You can be all like, look how good I am. So we've got our x, we've got our y. And again, if you wanted to, you could put it into an ordered pair. Just remember that x comes first. Oh, but remember, x and y stood for something, right? Like, x and y stood for something, didn't they? All right. So I would like you to interpret our solution. Like, we just found this 56 and 28. What are they? Interpret the solution in terms of the linear system. In terms of this problem situation, what is it that we just found, people? Go ahead and hit pause, write it down, hit play when you're ready to check your work. So the whole deal was that the school spirit club was selling 5-inch bracelets and 7-inch bracelets. And we said X was the 5-inch guys and that Y was the 7-inch guys. So what this means is that the school spirit club plans to make a total of 56 5-inch bracelets and 28 7-inch friendship bracelets. Yay. Always good to know what you're talking about, right? We did all that work. We got to make sure we know what it is that we found. So let's do the talk of the talk real quick. We have now used 3 different methods for solving systems of equations: graphing, substitution, and linear combinations, all right? The graphing method, what's good about it? What's bad about it? When is it a good time to use the graphing method? Maybe that's a great question to ask. So describe how to use each method, the characteristics of the system that would make the method most appropriate. What has to be true about your equations that would make it easiest to use that lovely method for graphing, for substitution, and for linear combinations. Go ahead and hit pause, jot down your thoughts here, and then hit play, and we'll keep the discussion going. So the graphing method. So that was where we graph the two lines. So first I'm describing what it is. We graph the two lines and we identify the intersection point. This is where they hit. Yay. The issue with this method is, first of all, sometimes it can be hard to graph them. I get that. The other issue is that sometimes you've noticed on some of the problems we've done, sometimes you only get an estimate of what your intersection point is, right? If you're not using Desmos, if you're just using graph paper and straight lines, sometimes you're like, I think that's where that point is. It kind of looks like it's there. It gets kind of hard and you end up guessing a little bit, right? But it's a great method because you can see it, right? That's my answer. It's right there. So this method is most appropriate when the equations are easy to graph, when the equations are written in general form, right? That whole like y equals mx plus b. When your equations are written like that, that's usually when it's a good time to use the graphing method. And also, of course, if your values are reasonable to graph. If my y-intercept is 4,362,573, I probably don't want to use the graphing method. So again, graphing method is great when you have equations that are easy to graph. It's in general form, the numbers are reasonable, that kind of a thing. Substitution method. All right, so this was the method where you got a variable alone and then you plugged into the other equation. So you choose one equation, you isolate the variable, so it's just x equals or y equals, and of course then you can take that and substitute it into the second equation. And that means you can solve the new equation with only one variable, and then use substitution again to plug back in and find that second variable. So substitution is nice. Substitution will do the job, right? You just plug stuff, get a variable alone and plug stuff in. That's manageable. And it's most appropriate when at least one of the equations is written in general form. Because take a look, if it's already written in general form, it's already a y equals. And so anywhere you see y, you can plug in this other stuff. You can substitute in right away. So usually if I see at least one equation in general form, I kind of lean toward the substitution method, right? Because I can just substitute in for y and solve for x. Now, the linear combinations method. It's my favorite. It's one of my favorites. But of course, certain things have to apply in order for it to be one of my favorites. Now, first of all, the method itself. That's where we rewrite one or both of the equations so that the coefficients of one of the variables are additive inverses, right? That's where I make sure I've got opposites for x or I have opposites for y so that I can then add the two equations, kill one of those variables off, and it results in an equation in one variable. So I can solve the new equation with only one variable and then, of course, substitute back in to solve for the second variable. Now, I love the linear combinations method, but keep in mind it's most appropriate when both equations are written in standard form, right? That whole ax plus by equals c. So if I see that my equations are both written in standard form, that's when I'm going for that linear combinations method. That's when I'm like, ooh, let's get some additive inverses going on, some opposites, and add our equations together so we can make things cancel out. Die. We're so vicious in math and algebra. It can't be helped. All right, guys. So now we've got our three methods. We've got three methods. As always, I hope you found this helpful and I hope you found this useful. If you have questions or concerns, please feel free to talk to me. Talk to me during class, talk to me after class, come see me during office hours, come talk to me and I can help you out. And I'll see you later. Bye.